Hi there, this is Jude Socrates. Welcome to today's video where we will talk about moments and centroids. So we're going to take a region on the plane and we're going to look for its centroid, or what is sometimes referred to as the center of gravity. And that's a more general term when the region does not have a uniform density. But for us, we'll just call it centroid for short. So I'm going to pause the video and I'm going to show you physically what we're going to do today. Whoa! So we're actually going to be doing something like a balancing act. So I have some shapes here with me. Let's start with a disc, okay? If you like a circle, where of course it's filled in inside. We're literally going to try to find with our finger, where should our finger be so that the disc is perfectly balanced. And of course, you can easily guess that that should be at the center of the circle. Okay, so I have a little water bottle here with me. Let me back up a little bit. Put the keyboard out of the way. Here we go. So that would represent my finger, and it is easy to balance it this way. Okay, so there we go. And the disc is balanced. It's not wobbling in any direction. Okay, so similarly with the rectangle, and we're going to use this for a different purpose in a little bit, you can look for the center of the rectangle, and that should be where you should position it. Woohoo! There we go, so that it's more or less perfectly balanced. Okay. Now, what if you have something like a right triangle? Okay, so this one's a little bit trickier. Yeah, if it were a complete rectangle, we'll put it at the center. Obviously, that's not gonna work. So let's see. Should it be closer to the right side or the left? Looks like it's gonna be heavier over here. So let's try over here. And still wobbling a little bit, and almost there. Okay, that's about as stable as I can get it. So if I put my finger over there, that should be where the center of gravity is. Okay, so it's pretty obvious that's not halfway between the right angle and this vertex, or this right angle and the top vertex. Okay, so it's definitely not 1/2, but it is a nice fraction. And you might want to start to wonder, okay, what could that fraction be? All right, same thing. If instead of a full disk, we had half a disk, half a circle. Okay, so you can, of course, take any cardboard box and make your own model. And again, we are assuming that the material that the region is made of is uniform. In other words, if I take a little square here and little square here of the same size and put them together, I can't tell them apart. Okay, they're going to weigh the same, they're going to look the same. Okay, so how would we balance this? So by symmetry, it should be somewhere along the central axis of the disk, or the half disk rather. Okay, so should it be closer to the top or to the bottom? Well, this is the halfway point, and it's clearly tilting this way. So it should be closer to the bottom. So there we go. And again, if I put my finger over there, that should be where the center of gravity of this half disk should be. Okay, so that's the idea behind today's video. And I'm going to pause it because we're going to talk about the basic or one-dimensional case. Okay, so I put the water bottle away for a while. I'm going to try to balance this ruler, not at the center, but on the left over here. Okay, so I'm going to try to keep it stable because I'm going to put some friends of mine up here. Right, so here's one of them. So obviously that's going to tilt it this way. And here's a much bigger friend over here. And ooh, gosh, he's heavy. Okay, so I need to find where should I put, whoops. Let me stop for a while and let me stick them to the ruler. There we go. Certainly they're not going to move anymore because I put some invisible tape on it. So again, I'm trying to balance it over here, but how am I going to do that? I'm going to have to put my finger somewhere, most likely between them, so that it's not going to wobble anymore. So would you believe that my finger should be closer to the heavier guy than to the smaller guy? Okay, so I need two hands to do this. So I'm going to bring the water bottle back. And let's see now, where should it be so that it is stable? Okay, ooh, there you go. Okay, I'm going to keep my hands close by. So is it exactly in between? I don't think so. It looks like it's closer to this big guy than to the other guy. Okay, I'm going to add another friend to our system. Okay, so I add a really big guy on this side. And we want to know, okay, how am I going to balance this thing? And it doesn't have a pedestal, so I just hope it doesn't fall. It should probably be closer. Yep. It's still, okay, there you go. Now it's getting there where it's just about balanced. I'm not going to move my hand too far away, as you can see. Oh, there it is. Okay, there you go. Definitely the centroid of the system should be closer to the big guy, this big guy, than to this big guy. Okay, so of course there's some physics involved over here. If I knew how heavy each of these three guys are, then I can compute. I can literally compute where should we put our support so that it's perfectly balanced. Speaking of support, if I knew these three weights, how heavy these three guys are, then Newton's first law says every action has an equal and opposite reaction. So these three guys have three weights, and the bottle is supporting the three weights. Okay, so we're going to use that to compute where should this point be located. Okay, pause time. All right, so back to the small screen. We're going to represent our regions, our plates, using, of course, a function. So we have a function, y equals f of x, and as usual, we'll restrict it between x equals a and x equals b. So this is the plate that we want balanced. So yeah, if I cut this out of cardboard, I should probably put my finger somewhere around here so that it will be perfectly balanced. Okay, so where would that centroid x bar, y bar be located? So we're going to develop formulas for them. As usual, they will involve an integral. Actually, they will involve two integrals. And if you put them together, three integrals total. Okay, so we said, all right, to understand what's going on, we have to learn how to balance objects which are simply living on a line segment, like our three friends over there. So what that means is we need to understand the concept of a moment. Okay, so that sounds like time, okay, a moment in time, but actually no. In this case, the physical meaning is a force multiplied by distance from the fulcrum. So maybe if I just carry our friends back a little bit, okay? So each of them has a weight. They will have different weights, and they also have different distances from the fulcrum. The fulcrum would be that point on the left, okay? But I also have the water bottle, which is pushing upwards, okay? So as far as the fulcrum is concerned, the three guys over here are trying to rotate it this way. I would call that clockwise from my perspective. From your perspective, it looks counterclockwise. It's trying to swing this way. The water bottle is going to push it from the other direction, okay? So as far as my perspective is concerned, it looks like a counterclockwise direction. From your viewpoint, it looks like a clockwise direction. In either case, the moments of the three guys are going in one rotational direction, and the water bottle is pushing it in the opposite rotational direction. Okay? So a moment can be positive or negative. Okay? So maybe I should put a plus or minus sign over there. There we go. So depending on the way that the force is making the system rotate. Okay, so for the sake of convention, as in trigonometry, let's say that counterclockwise rotations are positive and clockwise rotations are negative. Okay, so first let's analyze the system that relates to these three guys, and that will help us to understand what to do for a plate like this. All right, so let me use GeoGebra to model what it is that we are doing with these three friends sitting on my ruler. Okay, so I will represent the ruler with a line segment. Okay, I could have gone all the way to 12 or 12 inches or whatever, but this is just to illustrate the idea. So the ruler is going from 0 to 5. I have three guys sitting on the ruler. One more thing, the ruler is thin plastic, so we can assume it has very negligible mass or weight. Okay, so it's just a platform for them to stand on, and they don't really affect our computations. We can ignore them. Okay, so the length of these arrows represent the variability of their weights. Okay, the big guy is obviously the heaviest, so we have the little guy in the middle and the medium guy towards the right. Okay, so we said that for this to be perfectly balanced, number one, the bottle is going to support the weight of the three objects. Okay, so this green vector, and that's what it is, a vector, is pointing in the opposite direction because, again, these three are causing a rotation in one direction, but the finger, the water bottle, is causing it in the opposite direction. Okay? So first things first, the sum of the three lengths over here should be the length of this arrow. Okay? So in other words, the sum of the three weights of those objects must be the force which the water bottle is exerting in the opposite direction. Newton's first law. But now, this is where moments come in. It is not enough that the bottle is supporting the entire weight. We could pound the ruler onto the bottle and it'll support it. We don't want it to rotate. That's our main goal. Okay? So what's going to happen? We have a moment here, this weight multiplied by this distance, which in our case, for example, is 1. And then this other weight multiplied by this distance, and this third weight multiplied by this distance. So even though these guys are lighter, because their distance is greater, their moments might be not too far from the moment of this guy. Okay, so if we were to use the actual numbers, the moment of this guy is 2 times 1, but the moment of this guy will be 1.5 times 4. Oh, so actually it's greater. Okay, and this guy will have moment 3 times 1. Now, direction. So these are going, we now have the same perspective. They are going in a clockwise direction, so they will have negative moments, but our force will have a counterclockwise tendency to rotate our ruler. Okay, so these will have negative moments. This will have a positive moment. So for the system to be perfectly balanced, the sum of the moments must equal 0. Back to our work group. All right, so now we can find the actual location of the centroid, and we'll do it in an abstract way because this is how we're going to do it for our problem of finding the center of gravity or centroid of an arbitrary plate. Okay, so So the ruler has negligible mass. We can ignore it from our computations. We have three objects, different weights, W1, W2, and W3, different distances from our fulcrum. So let's call them D1, D2, and D3. We said that the bottle has to exert a force equal to the total weight of our system. So F is W1 plus W2 plus W3. And of course, it's pointing in the opposite direction, hence producing a moment which is of opposite sign as these three weights. Okay, we want to know where should we put this force F along our ruler. Okay, so we don't know what D is from the fulcrum. So to solve for it, we need to satisfy an equation. Okay, so we said that F is producing a counterclockwise rotation, so its moment is positive. So its moment is force, which is these three, times D, which we don't know. Okay? To achieve balance, the total moments acting on the system should add up to 0. Okay? So these three weights are going to produce negative moments in the clockwise direction. So it'll be minus W1 D1, minus W2 D2, and minus W3 D3. Okay, so water bottle counterclockwise, three guys clockwise, negative. Their moments should add up to 0. Okay, so there we go. We can now solve for D. We can put these three guys on the other side. So let me copy this, and this turns into an equals, and these are pluses instead of minuses. Okay, there we go. And of course, to solve for D, we just divide the right side by the total weight. Okay, so let me put this into a fraction. You're over there, and we'll divide by the total weight, which is underneath there. Okay, so this is basically the model that we are going to use to analyze those regions that we have. And again, we're going to use calculus. So in calculus, integral calculus, the idea is always simple. Split up the problem into small parts, understand each part, take a summation, go to infinity. All right, so let's just briefly go back to the statement of our problem. We have a function between A and B, and we want to know where is its centroid. If we were to cut this out in cardboard and actually put our finger somewhere there to find where it will balance. Okay, so here comes the calculus. We will subdivide the interval from A to B into n equal pieces as usual. The width of each piece is delta x, b minus a over n. And then this will enable us to partition our interval into x0 starting at A, x1, x2 up to xn, finishing at B. We will look at each rectangle that we will form between xi minus 1 and xi. Okay, so here are the rectangles. Let me scoot further down. Within each sub-rectangle, we're going to choose a representative. So to keep it simple, I am choosing the right endpoint of each sub-interval as my representative. Okay, so the height of each rectangle is determined by xi, so that's f of x1, f of x2, f of x3, and so on. And we will assume that the density is constant. Okay, so again, if I take a small square here or a small square there or there, I cannot tell them apart if they have the same size. The material that this region is made of is uniform, homogeneous, you might say. Okay, so of course, to find the weight of this rectangle, we will need its area. And the area is, of course, the height, f of xi, times the base, which is delta x. All right, so we saw when we solved for d a couple of minutes ago, we found the fraction, and in the denominator we had w1 plus w2 plus w3, the total weight of our system. So similarly, we want to know the total weight of our plate, right? So for simplicity, we'll assume that the weight density is 1, just to keep it simple, and that 1 means newtons per square meter, if 1 unit on our Cartesian system corresponds to 1 meter. It really doesn't matter, because as long as we're consistent, same units, we're fine. Okay, so the weight of each subrectangle will be its area times its density of 1. So basically, it just looks like that's the area of the rectangle. Okay, so in other words, we're not going to worry about density. Okay, we'll just stick to area. So what is the total weight of the plate? We will add up all of the weights of each subrectangle, take the limit as n goes to infinity. Wait a minute, we know the fundamental theorem of calculus and how to define a definite integral. That looks like the definite integral of f of x dx. Okay, so yeah, isn't that just the total area of the region? Sure. Okay, but that's because the density, we assumed it to be 1. Okay, so that is one of the integrals that we're going to need to find x bar and y bar, because, again, in our computations earlier, the weight of the 3 guys was in the denominator. Okay, so now that we know how heavy each rectangle is, we're going to study its moments about 2 axes this time. Because we have a 2-dimensional object, we're going to need a moment with respect to the x-axis and with respect to the y-axis. 2 moments. Okay? So we are going to cheat the way physicists cheat, and that is we're going to compress that entire rectangle into a single point. Okay? What a physicist would call a point mass. And of course, since we have a rectangle, the most logical place to put that rectangle is at the center of the rectangle. Okay, so I kind of am sneaking something in here. We use the right endpoint to approximate the height of a rectangle, but I want to locate that point at the middle. Okay, so I'm going to use a symbol xi bar to mean the center, the midpoint of xi minus 1 and xi. Okay, the difference is very, very small. It's half of delta x. Okay, so it's not really going to affect our computations because, of course, the number of intervals n is going to infinity. Delta x is getting close to 0. Okay, we're going to go back to GeoGebra so that you can see what's happening to these rectangles. All right, so here is our region and our rectangles. How many do we have? 3, 4, 5, 6, 7, 9. We got 12 subrectangles. And we are going to pretend that each of these subrectangles is squished to a single point. Okay, so that point will be somewhere here in the middle. That's almost 8, so this will be almost at 4. Okay, and we'll locate it at the midpoint of this, of the base. All right, so similarly, like here, for example, or here's a good one. Okay, so that's almost 4. So the weight will be concentrated at around 2 at the middle of that subinterval. Okay, so I'm going to literally pull a curtain on you because I have, ooh, here it comes, here it comes, here it comes. I have a 3-dimensional version of what's happening here. Okay, so let me rotate it a little bit. Yeah, there you go. And shrink it. Oh, there it is. Okay, I like that. So we have here, we can see the x-axis and the y-axis. And yes, I'm drawing this in space because that's what's happening. Okay, this triangle is on the tabletop. Okay, but it's trying to rotate like this and to rotate like this. 2 axes of rotation. One about the x-axis and one about the y-axis. Okay, so you see these dotted lines. Okay, those are arrows. Okay, those are vectors. those represent the weight of each of these rectangles. And again, it's controlled by the area. All right. So from this direction, you have a light rectangle close to the fulcrum, and the rectangles are getting heavier and growing farther away from the fulcrum. Okay, that's when the x-axis is the fulcrum of rotation. So now let's turn it this way and look in the direction of the x-axis. Okay, so I'm going to rotate it this, and now it is flat again. And it's always tricky, try to get it perfect. Okay, that's almost as perfect as it's going to get. So this time, the heavy rectangles, which are these ones, are closer to the fulcrum, which is the y-axis. You don't see the y-axis anymore because it has been compressed to a single point. Okay, so these arrows are like those three guys on the ruler. Okay, each one of them has a weight. Each one of them has a distance from the fulcrum. So in the case where our fulcrum is the y-axis, their distance is just xi bar, or let's not split hairs, literally, it's just xi. Okay, and in the case of when the fulcrum is the x-axis, then the distance is 1/2 of f of xi. Okay, so we're going to use those in order to find our x bar and y bar. All right, so I mentioned earlier that we will need 3 integrals to find x bar and y bar. I said one of those integrals is the area of the region, which actually represents its total weight. But here come the 2 other integrals. They will come, of course, from the moments of each subrectangle with respect to the x-axis and with respect to the y-axis. So the ith rectangle is at a distance of half of the height from the x-axis. And again, we're thinking of it as a point mass, but its distance from the y-axis is the right endpoint, xi. And technically, it should be the midpoint, but let's just make it the right endpoint. They're very, very close to each other. Okay, so now we are ready to compute each moment, one with respect to the x-axis, one with respect to the y-axis. So the weight of the ith subrectangle is f of xi delta x, its area. So that's what's in both of these formulas. The distance from the x-axis, we said, is 1/2 f of xi. The distance from the y-axis is xi. Okay. So multiply and simplify, we see an f of xi squared delta x with a 1/2, and we simply see an xi times f of xi delta x. Okay, so that's the moment of each subrectangle. Take the Riemann sum of each, make the limit of n goes to infinity. Voila, we have 2 definite integrals. So this represents the total moment of our plate around the x-axis, and this represents the total moment of the plate about the y-axis. I'm back. So this is going to be our first example. We have a right triangle, and let's assume that this distance is a. So this will be at a0, and this distance is b. So that's going to be at 0b. We're looking for the centroid of our triangle. So if I did that right, and maybe I should have measured it first. Yeah, I think I'm close. Okay, so this is like the water bottle, okay, pushing in the opposite direction as the weight of the triangle. Okay, how far is the finger, the centroid, from the x-axis? Well, that's the y-axis. Well, that would be the x bar coordinate. How far is it from the x-axis? That would be the y bar coordinate. Okay, so we are now ready to solve for x bar and y bar. All right, so if our finger is correctly positioned at the centroid, it is supporting the entire weight of the plate. And we said that the weight is the integral from a to b of the function also known as the area because the density is 1. Okay, so the finger also has a moment with respect to both the x-axis and the y-axis, okay? But the distance from the x-axis is y bar, and the distance from the y-axis is x bar. So the moment of the finger across the x-axis is the weight of the plate times y bar, and the moment about the y-axis is the weight of the plate times x bar. So we saw how, when we had only the 3 weights, we could put them to the other side and divide by the total weight of our system. So similarly, we can put our moment for the plate on one side, and that should equal the moment, the corresponding moment for our finger on the other side. Okay, this was the moment about the x-axis for the plate. This is the moment for the about the x-axis for our finger. Similarly, the moment of the plate with respect to the y-axis, and this is the moment of the finger about the y-axis. So there we go. Last step, divide by the total weight of our system, just like how we saw the fraction over W1 plus W2 plus W3. Okay, so we have the formulas in all its glory. We want 3 integrals. And of course, the denominator, you only have to do it once. Find the area of the region. Find the integral of the function multiplied by x from a to b. And please, 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 these do not cancel. That's the worst mistake you can ever make, and frankly, completely stupid. Okay, don't be stupid. Do not cancel the f of x. Oh, it's just 1. Yeah, good luck with that. Similarly here, you square the function first, then integrate, divide the answer by 2. Take half of it. Take both of those and divide by the total weight or the area of the plate. That is your x bar and your y bar. Okay, let's do the triangle. All right, so here is our right triangle, kind of like this one. We're facing the same way. So our vertices will be the origin, of course, where the right angle is going to be, A0 and 0B. So in this case, A is 4 and B is 6. Okay, so we want to know, where is the centroid, where's the exact centroid of this right triangle? All right, so we're going to have those 3 integrals. Let me copy them and integrate. Oh, wait, we need a function. So we need a function. Let me save that for later. All right, so our function is this line, and just need slope and intercept. Oh, we already have the y-intercept. So the slope is b over a, rise over run, except it's going downwards. Okay, so the equation should be negative b over a. Let's make a fraction. B over ax. The y-intercept is b. Okay, so yeah, if you want to simplify that a little bit, yeah, let's factor out the b over a completely. So take out the b over a, and you'll get negative x plus 1. Oh, not plus 1, but a. So that's a minus x. Okay, double check. Distribute b over a times a gets b. B over a times minus x minus b over ax. Okay, so that is our function, and that's the function that we are going to plug into our 3 integrals. Okay, well, let's start in the denominator. Wait, that's just the area. We know how to find the area of a triangle. So the area is simply 1/2 base times height, isn't it? So 1/2, the base is a, the height is b. Okay, 1/2 ab. Great. So now, oh yes, my apologies. In this notation, a and b are the left and right endpoints of our interval. Okay, so in our case, we need to integrate from 0 to a. All right, so that is the domain of our function. Okay, so where 0 is less than or equal 2x and less than or equal to a. That is our domain of integration. Okay, glad we settled that. So now we get to integrate the numerators. So we have integral from 0 to a, 0 to a, x f of x. So our f of x is this. We can copy that, and we have this. So yeah, that's not very difficult to integrate. You don't need a trig sub or anything, but you should have the correct limits from 0 to a. Okay, so we can take out the constant. That's just b over a there. And why don't we distribute this? So that is ax minus x squared. Okay, and I guess we should wrap that in parentheses. And we're ready for the antiderivative. So let's put that in brackets. Ax becomes ax squared over 2. And x squared becomes x cubed over 3. Divided by 3. Integrated from 0 to a. Okay, so what have we got? 0 goes away, thank you. When x is a, we get a cubed over 2. Oh, interesting. A cubed over 2. And when x is a, we get a cubed over 3. Oh, wow. Okay. So there we go. And we have simplified. We're going to get 1/2 minus 1/3. 3 minus 2 is 1 divided by 6. Oh, a cubed over 6. Excellent. And wait a minute. We have an a also in the denominator, so we get to cancel. Okay, so we're left with just b on the outside and a squared over 6. Okay, so similarly, let's get the numerator for the second integral. So we need, I need a copy of this because we already have the correct limits there. And this time we want 1/2 f of x squared. Okay, so we'll put that there, 0 to a. Our f of x is this, and we're going to square it. Okay, so this time you're going to get b squared over a squared, and there's a 2 in the denominator. So we get b squared, a squared, and a 2. And we're going to expand a minus x quantity squared. So that sticks around. We need to get rid of these. Let's square. Okay, so we're gonna get a squared minus 2ax plus x squared. Right on, right on. Okay, antiderivative. So we will take this away and take this away and put this in braces. Antiderivative, a squared becomes a cubed over 3. Sounds familiar. I'm sorry. Stupid, very, very stupid. Bad. Bad. A squared is a constant with respect to x. Okay? So that correct integral is a squared x. Okay. So similarly, minus 2a is a constant. We're integrating with respect to x. So we have x squared over 2. Finally, for x squared, we have x cubed over 3. Again, evaluated from 0 to a. So can I copy this? Oh yeah, thank you. All right, at 0, does everything go away? Yes, everything goes away. So we just have to plug in x equals a. So now that becomes a cubed. And then 2a a squared, so that's 2a cubed over 2. Oh, nice, nice. So that goes away. Why didn't I see that earlier? Okay, ooh, that cancels. And then you have a cubed over 3. All right, so great. These two are going to cancel. And we're going to get just a cubed over 3. And, oh, check it out. So the a squares gonna go away. And we're gonna be left with a in the numerator. And that's gonna go away. And 1/2 and 1/3. Oh, 1/6. 6. Okay, so the a stays in the numerator. Okay, let's look back to what we did for the first numerator, this one. We are left with ba squared over 6. Here it's backwards. It's ab squared over 6. Okay, that kind of makes sense because, yeah, it should be just as easy to do this as it is to do this. Okay, there should be really no difference. It's not symmetric, but yeah, they do have analogous roles. Okay, so we are now ready to find our x bar and y bar. Okay, so our area is this, so let me copy that down here because I will probably lose the top of the page there. Oh, what do you know? Okay, so let's put y bar down. Ooh, that looks nice. So we're gonna get in our numerator our first integral, which is this, b times a squared over 6. And the denominator is the area, 1/2 AB. So we're going to get, whoops, not all the way, just that. Okay, so what's going to cancel? The b's are going to cancel. One of the a's is going to cancel. So let's do that slowly. Go away b, which means that the brackets can go away. Go away b, and then one of the a's will go away. Goodbye and goodbye. Okay, so we have 1/2 in the denominator, flip it up as 2 in the numerator, 2a over 6. Ooh, that is simply, let's write it nicely, that is simply 1/3 of a. Okay, so similarly, for y bar, we want the same denominator, so I'm going to copy this, but the numerator should be ab squared over 6. Come on. Just this much. Okay, so once again, what's going to cancel? What will remain? Okay, so the a's are going away completely. And one of the b's is going away. So b, ooh, look at that. So b over 6 times 2. And the final answer is 1/3 of b. Okay, so that kind of makes sense. Okay, so remember our diagram, our model over here. That is not 1/2, but that is 1/3. 1/3 of the base. Can you actually measure along? So okay, maybe I cheated a little bit. Okay, but you get the idea. So similarly here, that's about 1/3, 1/3, 1/3. Okay, so those are the exact centroids for a right triangle. All right, so we had the half disk, and we want to know where's the centroid of that half disk. We will represent it as the upper half of x squared plus y squared is r squared. Here r is 4. So solving for the upper half, our function is square root of r squared minus x squared. Okay, so by symmetry, the centroid should be somewhere along the y-axis. So therefore, we only need to find y bar. X bar is going to be 0. One way to think about it is that a rectangle here at 2, for example, will have a clockwise moment, but you have an equal triangle of the same size on the other side that will have a counterclockwise moment, and they come in pairs. Okay, so therefore, the two moments will cancel each other out. Okay, so we only need the formula for y bar. And do we have y bar? Yes, it's right over here. That's all that we need to do this problem. Okay, so let's copy that over here. All right, so we will also save that for later. We have that formula for y bar, and of course this is the area of the semicircle, and everyone knows that that area is pi r squared, but we have half pi r squared divided by 2. Okay, so that is our area. To get the numerator, we need to square our function and integrate from a to b. Oh, once again, our limits are wrong. We're going from negative, oh, wait a minute, who are these? This is the radius, okay? So we're going from negative r to positive r, okay? And might as well keep working here because we already have the denominator. So this is just the area, and we have pi r squared in our denominator. Okay, there you go. Who is our function again? It is here, square root of r squared minus x squared. And get back down. We are going to square it. Okay, so of course, when you square a square root, inverse functions, the square root goes away, the square goes away. Okay, so what do we do? I guess we can take the, oh wait, check it out. We have a 1/2 here. We also have a 1/2 here in the denominator. So both of those 1/2s go away. Cancel. Excellent. So we have the full area of the circle in the denominator for now. And we need to integrate the numerator. Okay, so we are doing, okay, again, with respect to x, r is a constant with respect to x. So that antiderivative is r squared x, and x squared becomes x cubed over 3. We are integrating from negative r to positive r. All right, and yeah, we don't have 0 this time. Could we have gone 0? Honestly, yes, because this is an even function. Do we get an even function? Yes, power 0, power 2. We could have replaced minus r to r with 0 to r and doubled the answer. Okay, well, little too late, but it's okay. It's not that hard. So r squared times r, which is r cubed, and r cubed over 3. Okay, so that is for positive r, and then minus, we have to do the same thing for negative r. Okay, so we'll copy that over here, and at negative r, you get negative r cubed. Watch those minuses, they bite. And then minus r cubed, so that's going to be plus r cubed. Okay, remember how I said double? We just double the answer. And you can literally, whoops, you can literally see that forming before our very eyes. Because we have r cubed minus plus r cubed. So that's going to be 2r cubed. We have accounted for that. And we have minus r cubed over 3 minus r cubed over 3. So that's also double. Okay, so it's as if we had integrated this, yes, r squared x minus x cubed over 3, but doubled from 0 to r. Oh, isn't that special? So what do we get? R cubed, and we have 6 minus 2, 4/3 r cubed in the numerator. So we have 4r cubed over 3, put 4 there, over 3. Double check. 6 minus 2 is 4 all over 3. Okay, what cancels? R squared. That's about the only thing that we can cancel. Cancel the r squared, goodbye, and the r cubed becomes just r. Oh, okay, there we go. And just to make it pretty, let us get out of the way. Let's see our, oops, sorry. There we go. So yeah, just to make it look nice, let's put the 1/3 in the denominator. So it's 4r over 3 pi. Okay, so there you go. It's not 1/2. That's definitely not 1/2. Is it bigger than 1/2 or smaller than 1/2? So let's see. Let's ignore the r. And 4 over 3 pi is approximately 0.424. So it's slightly smaller than 1/2. Okay, there you go. So that we did the right triangle, we did the half circle, half disc. Now, we basically did the computations when we only had one function, right? But as usual in calculus, sometimes you have a function above, you have another function below. So when that happens, how do we modify the formula for x bar and y bar? Okay, very easy. So first of all, you need the area of the region in the denominator, just like we had. Okay, so this time the height of the rectangles are f of x minus g of x. You've done that since basic integral calculus. Okay, the distance from the rectangle to the y-axis is still x, xi to be more precise. So the numerator for x bar is the same integral where we had f of x times x, but this time there's a minus g of x. Okay? This one is a little bit trickier to understand, and I want to explain it to you. Okay? It kind of makes sense that if this was the original integral by hiding the g of x, then we should have the original integral, but it is paired with also g of x, where we square g of x as well, just like we do with f of x, okay? But that does deserve some explanation, okay? So the area of the ith subrectangle is now, copy this, so we have that, and I'll keep the braces. F of xi minus g of xi. Okay? So we said that the distance from this rectangle to the y-axis is still xi. Okay, so that's why that doesn't change. But why is there now a square here minus square here? Why don't we take the difference and then square the whole thing, right? Wouldn't that be a natural generalization as well, okay? But now, however, the rectangle, when we concentrate this rectangle into a point mass, okay, so remember what we did. We squished the rectangle into a point located halfway through that rectangle, okay? So now, we have a rectangle, but at the top we are at f of x, at the bottom we are at g of x. We want the midpoint. We know how to take a midpoint, take the average, okay? So into a point mass at height, take the average. So f of x minus, instead of minus g of x, take half and divide by 2. Okay, so the location of that centroid is now at f of xi plus g of xi divided by 2. Average location. Okay, so therefore, the moment of this subrectangle about the x-axis is thus the product of the area with the distance. You see what's happening? A minus b, a plus b. That's a difference of squares. F of xi squared minus g of xi squared divided by 2. All right, so that's about it. Ooh, under an hour. I thought I would go over an hour on this one. So yeah, the idea is just about the same, but you have to make adjustments with your g of x. One more thing before we go. You remember when we did integration by parts and we learned how to sometimes integrate x ln of x or x e to the x or x sine of x? So that's going to happen to some of our regions. If you have a sine curve, for example, and you want your x bar, then you'll have to multiply x by sine of x to get this integral. All right, so that's about it for our video for today. So until next time, I hope you enjoy the rest of your day. Bye.